Attacks, applications of AI in cyber, and secure hardware design. He received a BS and master's degree in electronics and electrical electronics engineering from Ihsan Dogramaci Bilkent University, Turkey, in 2012 and 2014, respectively. He received his PhD in electrical and computer engineering from Worcester Polytechnic Institute in 2020. Dr. Brooke, it's extreme honor to have you at UND webinar series. I appreciate your time this morning with us. The floor is yours. You have about 45-50 minutes for your talk.
Thank you for the invitation and for the introduction. So let me share my screen quickly. Okay, so hello everyone. So I'm Dr. Gulmezoglu. I'm an assistant professor at the Iowa State University. So I'm associated with the CyIO Center here. And I'm going to talk about artificial intelligence applications for microarchitecture side channel attacks today. So like our current focus areas are mostly like discovering new microarchitectural attacks, like applications of artificial intelligence, machine learning, deep learning in hardware security, creating some more like secure and side channel secure cryptographic implementation, secure hardware design. I worked on cloud security as a PhD student in the past, and I'm still trying to work on this area as well. And finally, more like outside of cybersecurity, like image recognition for drone captured image. And these projects are mostly supported by Federal Aviation Administration and NSF. Currently, I have 3 PhD students, 3 master students, and 2 undergrad students working on these projects or the combinations of these projects. So the outline of the talk today, like first I'm gonna introduce you to side channel attacks and microarchitectural side channel attacks, because we need to understand the field, like what we are applying machine learning and AI into, like what is the area, what does the area look like? And then applications of machine learning and AI models in microarchitectural side channel attacks, because I saw that there are not many like informative presentations yet about the applications of machine learning and AI models in the microarchitectural side channel area. Like there are some talks about machine learning and AI in side channel attacks, and they are mostly covering physical side channel attacks, but there is not much guidance on machine learning and AI models for the microarchitectural side channel attacks. So it may take some time to introduce the field and what is going on in the field. And then we have 2 projects on this area, like variational autoencoders as a defense mechanism against website fingerprinting attacks. And the second one is generative adversarial networks and transformers usage for spectre attack gadget creation and detection. Depending on the time, the second one, generative adversarial networks one, may be skipped. We will see. And finally, I will talk about future directions of AI for microarchitectural side channel attacks. So first of all, I introduce side channel attacks. Like there are different types of side channel attacks. Most of them require physical access to the target device. Like for instance, in the power monitoring attacks, let me put the pointer here. So in the power monitoring attacks, we have an oscilloscope and then we have a target computer, and we are trying to see how the power consumption actually changes depending on the operations that we are having in the computer. Sometimes it would be a smart card and reader, and we are trying to see, okay, what is the power consumption, how it actually fluctuates depending on the specific operations that we are having in the computer. Another one is acoustic attacks. Like this one is also very interesting. For instance, like you are pressing lots of keys on your laptop and you are in a Zoom call, and from the microphone in your laptop, the person that's who is not there, who is in the Zoom call but not physically there, can still actually hear which keys that you are pressing, and based on the amplitude of that key presses, they can actually figure out, okay, which keystroke actually you are entering at that time. So there are also other types of examples for the acoustic attacks. You may also need to have some physical access to the target device, at least like maybe a few meters away and so on, depending on the microphones and so on. So it's possible to actually figure out what's going on your laptop as well with the acoustic attacks. The third one is electromagnetic attacks. It's mostly requiring a special device to actually collect those electromagnetic waves coming from your laptop, especially if your screen is changing. For instance, you are rendering a website, then these electromagnetic waves can be captured in the meantime, and then people can actually find out which website that you are visiting. And finally, microarchitectural attacks, and our talk will focus on microarchitectural attacks. It doesn't require any physical access. Like you can actually implement this attack in a cloud environment, in a server in a cloud environment, and this server might be in Europe while you are in the United States. The idea here is that like you are trying to find out whether there are any shared hardware components between different users in the same cloud server. And then you create your own software snippets. Then you are trying to figure out whether this software snippet execution changes depending on like time or power, while another victim is running some operations in the same server. So this is the idea, and I'll talk about more about those microarchitectural attacks, like what are the capabilities of those microarchitectural attacks and so on. So from now on, we are focusing on microarchitectural side channel attacks, and these attacks leverage specially crafted software snippets to leak secrets from concurrently running applications or host systems. So there are different surveys on these microarchitectural attacks, like because there are lots of different attacks right now. Maybe it started maybe around 15 years ago. People spent more and more time on, okay, what are those hardware components, how they are actually acting while someone is running some, code snippets in the hardware. And then they noticed that, okay, these hardware components are actually shared between different users. For instance, we have something called hyper-threading for a while in Intel devices. AMD is also on this path right now. Hyper-threading actually tells us, okay, we have lots of components in one CPU core, like branch prediction unit, cache levels, and so on. And these are shared between two programs or two software snippets running at the same time. And these software snippets may not belong to the same application. For instance, you are using your laptop. There might be an application, let's say Zoom application, and you have another application, browser application running in the same core at the same time. And you don't know exactly what your Zoom call is actually collecting in the background. So it means, can it actually find out what is the website rendering doing in these components, how these components are actually used by that browser. In the meantime, the Zoom application can actually monitor that one and so on. So there are different types of attack scenarios. Cross-core attacks means, okay, we have multiple cores in our laptops, 4 different cores, 8 different cores, and you can also run attacks or perform some attacks between different cores as well, because there are some components that we see here shared between different CPU cores. And also you can get some information from the kernel as well as a user space application. So it means maybe a Zoom application can actually read your passwords from the kernel as well. And this was also a very dangerous attack, and we saw that with the meltdown attacks, if you heard about that. There are different targets for these attacks, like cryptographic libraries. I think this is the first target. Malicious applications are trying to leak secret keys. It might be AES key, RSA key, post-quantum cryptographic key, some secret that we are trying to leak based on the usage of those cryptographic implementations and the hardware components. Browsers. So this is also a very popular target. In this case, people or the malicious people, let's say, are trying to figure out which website that you are accessing. Most of the time, there are a specific set of websites the attacker is interested, and then the attacker is trying to figure out whether one of those websites is accessed by the victim. Machine learning models, it's getting more and more popular right now because we see that machine learning models are becoming IP, so intellectual property, and companies don't want to, leave or release the internal of those machine learning models. It might be like the number of layers, which layers are there, what are the weights or the hyperparameters and so on. And nowadays, these machine learning models are a target for the malicious actors who are using microarchitecture side channel attacks. And finally, keystroke detection, like can an attacker actually find out which password you are entering into your banking application on your mobile phone, as an example. So based on some properties of these keystrokes, it's possible to find out which keys are pressed or which combinations are pressed. There are different attack primitives in these types of attacks. The first primitive comes to mind is the timing. Like we are having some very high resolution timers. This is called like read timestamp counter RDTSC that comes with x86 assembly, and it's giving you a very high resolution timing information about some operations that we are having in hardware. And also power operating system features that are coming from the like the Windows operating system or Linux operating system that user space applications can access. So the question here is, why do attackers and side channel attackers most of the time leverage machine learning and AI in microarchitectural attacks? There are specific reasons. The first one is noise reduction. For instance, we are in a cloud environment. One virtual machine is trying to leak some information related to another virtual machine. However, there are also other virtual machines running at the same time in the same server. In that case, the other virtual machines that the attacker is not interested, they create lots of noise. It might be, again, like other applications in your laptop environment, or operating system runs and does lots of different operations. In that case, we have lots of noise in the side channel traces. And noise reduction is one of the primary goals of AI and machine learning in these types of attacks, like get rid of all the noise and only capture the useful information related to other virtual machines. The second one is, okay, let's assume that we were able to get rid of the noise. We also need to get some features, because sometimes these side channel traces are very long. For instance, for the website classification, the attacker monitors website rendering for 30 seconds, and it would lead to maybe thousands of samples in one side channel trace. In that case, we would like to get more useful features and extract some features from these traces related to specific websites. So this is also another primary goal of my machine learning and AI. The third one is scalability. Like, okay, we have, for instance, 100 websites that we are interested, but what if we have 1,000, 10,000 websites that we are interested? Can we actually scale it for more and more complicated scenarios? And AI and machine learning, they are very good at these types of tasks. Cryptographic key extraction, like, okay, we have lots of different key possibilities or combinations. Can we actually map those side channel traces after we extract those features to specific key possibilities or key candidates? And cross-device attacks, nowadays it's also a very big problem, and there are some approaches to that, but the problem here is that we have lots of different laptops or microarchitecture designs. So how an attacker can generalize an attack to multiple hardware platforms, so that with one machine learning model, you can attack different microarchitectural devices. So this is also another target. More adaptive attacks, microarchitectures, they are actually very complex. They have lots of components. In that case, can we make them more adaptive or like less noisy in this case as well? And finally, faster reverse engineering. Nowadays with LLMs, especially, like if you pass lots of information related to a specific microarchitecture design, can we actually learn more about that microarchitecture designs by using LLMs and get more or faster reverse engineering in that case, so that it's gonna help the attackers to create specific attacks for that specific hardware model. So I'll go through some specific attacks and how machine learning help in these scenarios. The first one is website fingerprinting attacks that I cover. So cache monitoring, like it means we are actually checking out how the last level cache is actually used while we are rendering some websites in a browser. So for instance, this is one of the examples by Zhang et al. In this paper, they are actually showing that, okay, we have power consumption data coming from Intel RAPL. And then, as you can see, they are collecting 20,000 samples for one website rendering. As we see, like there are lots of activities because at the beginning of the website rendering, you are downloading lots of images, text, and so on. So the power consumption increases and then it goes lower. Something happens at this point, and then again, it's most of the time low. It's also very similar in the cache monitoring, also frequency scaling. As an example, this is another paper, and this is coming from our lab. Like we are actually monitoring how the frequency of the mobile phones and laptops change for Facebook, Reddit, and Twitter. And as we see, each website has a different fingerprint, and these website fingerprint traces are given as an input to the machine learning model, and the machine learning model learns how these patterns change over time. We see that there are lots of different machine learning models have been used, like CNN, LSTMs, SVMs, KNN, and so on. This is why, like, deep learning models, actually, like attackers know how to use deep learning models for the website fingerprinting attacks. The second attack target is the application detection, like which application is actually running on your mobile phones or in the laptop environment or in the cloud environment. So in this case, cache monitoring and dynamic frequency have been used to execute these types of attacks. Again, we see that there are different fingerprints that we are collecting for different types of applications. And CNNs, SVMs, and autoencoders have been used for these types of attacks. Cryptographic key extraction attacks. This is a bit interesting because for the power side channel attacks, cryptographic key extraction is very popular, and then machine learning models have been used very heavily in power side channel attacks. However, in microarchitectural side channel attacks, people are not preferring to use it because most of the time we have one or two different cases. As an example here, we have square and multiply operations, and we have another operation that's called reduce operation for like ECDSA or like sometimes RSA applications or cryptography implementations. The attacker is trying to figure out whether there at a specific point in time we have a square operation, reduce operation, or multiply operation based on the timing that we get from the cache usage. And most of the time they are using supervised learning. We have square, multiply, and reduce. We only have 3 classes, and then we try to find out whether this is a specific operation or maybe multiple operations at the same time. So different different machine learning models have been used in this cryptographic key extraction attacks, like SVMs. For instance, for this one, SVMs can be used to distinguish those different operations, random forest, hidden Markov models, LSTMs, and also nowadays reinforcement learning becomes even more interesting for the attackers. Finally, we have keystroke detection attacks. There are 2 approaches in these types of attacks. One approach is actually here, and it's by Wang et al. They are actually trying to figure out, once we actually press a key on our laptop or on the screen, like visual keyboard, what's going on, like which libraries are actually running and which cache lines are actually accessed through these key presses, and then can we actually model it, like for instance in terms of time, and train a machine learning model with this information, and then try to predict the attacker's key presses. This is one of the scenarios. Another scenario is to collect all those different combinations of those key presses, and based on the timing between 2 key presses, can we guess what is this combination. For instance, here P and A, they are far away from each other, and then A and S, they are close to each other. SS, they are exactly two same key presses. So this is why the time difference is very low here. And then based on this information, can we guess the entered password based on the traces? So different machine learning models again have been used for these types of attacks, like random forest. KNN is very popular actually, like to find out like what is the time difference between two key presses, and also different APIs have been used to do these types of attacks, and decision tree random forest, they have been used. So since we only have the time difference between two key presses, deep learning models have not been selected for this type of attack because attackers think that this is not a very complicated task compared to website classification and so on. Finally, I'll talk about the defense approach. This is a very generic slide for the defense techniques, like or intrusion detection techniques. In this case, we have offline and online phases. So in the offline phase, the defender is actually trying to figure out, okay, what are different types of attacks and so on, or sometimes benign workload. And let's see how these workloads change the hardware component usage. Let's collect some performance counters, hardware performance counter values, train a model. It might be an RNN model, CNN model, or there are other types of models as well. And then in the online phase, can we detect any attack? Like for instance, in this figure at least, we have benign workloads. We are trying to detect some anomalies on the hardware, and these anomalies are the microarchitectural attacks. We learn the benign behavior with some recurrent neural network model. It would be LSTM or gated recurrent unit models. And then in the online phase, we see whether we see any anomalies in the hardware performance counters. Like this is the blue one here is the benign workload. And once we have an attack on this benign workload, we see that we are having actually some anomalies, and we are expected to detect this with less false positives and less false negatives so that we won't have any problems once we are employing this type of model in a real hardware. And different models again have been used, and deep learning models are heavily used in this type of defense techniques. The reason is that we are trying to lower the false positives, and deep learning models are actually performing better in terms of false positive rates. So, okay, I spent around 20 minutes for the generic introduction to see how AI have been used in microarchitectural attacks. I'll focus on a specific defense mechanism here actually. Like, can we actually use deep learning models to create some defenses against website fingerprinting attacks? So I'll give you a very short history of this website fingerprinting attacks. Dr. Yossi Eren in 2015 showed that there are lots of different tabs that we are having in a browser, and these tabs can actually figure out the cache usage in a very detailed manner. So it means you need to have a high resolution timer, and at that time the browsers actually provided a very high resolution timer. So it means you can actually create some code snippets, access lots of array elements, and measure the time for that array elements. Like how much time does it take to access all those array elements? And he showed that it's possible to detect which websites are actually running in the same browser from a different tab. And this is something very interesting because any website can do this attack. And then, of course, the browser providers didn't like these types of attacks. They decided, okay, we should lower the resolution. In that case, it's not easy to measure the access time for a specific cache line. Instead, again, Yossi Ören's team, this time his PhD student Schusterman, actually created a new type of attack. In this case, he's actually filling out the entire cache and then measure the time. For this type of attack, you don't need a very high resolution timer. And he showed that, okay, we can actually still detect the websites, 100 different websites with more than 90% success rate. And they showed that, okay, what if we actually create another website, and then this website will actually evict all those cache lines continuously as a defense mechanism. And in that case, they showed that the attack accuracy doesn't get very low. The reason is that the attacker can retrain the model with these noisy website fingerprints, and then these deep learning models are very powerful to detect the actual website fingerprint, even though there is some noise in that cache. So in that case, they had 78, 76% success rate for an attacker, and this defense mechanism didn't work very well in that case. There was another paper recently, and in this paper, this is from an MIT team, and they showed that actually these websites create some interrupts, and these interrupts are the main reason that we are actually seeing some timing variation in the cache monitoring attack. They also say that, okay, what if we increase the noise? Like if we send some artificial interrupts, they say that, okay, now we have 62% success rate and the attacker is still able to distinguish different websites. So these random noise approach don't work very well. In our case, we thought, okay, what if we actually use deep learning models and we intentionally change one website fingerprint to another website fingerprint? For instance, we are switching Amazon website fingerprint to Google website fingerprint, and we are gonna do this randomly every time a user is actually accessing Amazon.com. So it means one run, we are gonna switch it to Google website or Google website fingerprint. We will switch it to Facebook in another run, and so on. And we are trying to also make it less performance overhead, and we will see. So this is our mechanism. Again, the attacker collects all those website fingerprints. The defender is actually training a variation autoencoder and creates those noise templates. And these noise templates will be used in the online phase to switch one website fingerprint to another website fingerprint so that the attacker cannot distinguish which website is accessed by the user in this case. So our purpose is to obfuscate all those website fingerprints in real time. I'll briefly talk about prime and probe attack. I already talked about this a little bit, but we are using this cache occupancy channel scenario, and it's implemented as a JavaScript code in a web environment. Instead of measuring the timing of each individual cache sets, we are actually measuring the timing of accessing the whole cache. So if it's 8 megabyte cache, we are accessing, or we are creating an array with 8 megabyte of data, and then we are accessing each cache line one by one and see how much time it takes to access. And the timer resolution in this case is around 1 millisecond in Google Chrome browser as well. So how does it look like in terms of website fingerprints? So for instance, here we have Google, and as you can see, we have periodic high timings, but after the initial rendering, it's most of the time very low. And this is in milliseconds right now. So it means it's around 3 milliseconds, 2 to 3 milliseconds, if we don't have anything running in that browser. And then we have another one, NIH.gov. As we see, we have some periodic rendering. Probably the page is refreshing some images or some content. This is why we see some high variation in the cache usage, and then it goes lower. And we have Netflix. As you see, Netflix is very noisy. There is not a specific pattern, and the usage is most of the time very high in this case. So once we train a deep learning model with all these website fingerprints, and we have 100 measurements for each website, and in total we have 100 websites, we achieve around 95-96% success rate for Chrome and Firefox browsers. However, for the Tor browser, if you know, the Tor browser is more like a private browser. Like there's lots of noise in the network. The network latency is a bit weird. It's very high, and so on. And the accuracy is around 46% and 40% depending on the deep learning model. So this is very low compared to Firefox and Chrome, and still the attacker is able to distinguish with with still relatively high accuracy. So here we are using variational autoencoder. The reason is that the variational autoencoder works this way. We have an input, we have an encoder, and this encoder is like a feature extraction part. Like we are creating some mean and variance for this website fingerprint, for an individual website fingerprint, and then we have a latent vector here, and this latent space is actually capturing all those important features from a website fingerprint. And then we have a decoder. This decoder is trying to reconstruct the same website fingerprint that we have here based on the features here. And finally, we are checking the error between x and x prime and try to optimize this latent vector here. So this latent vector captures all those important features. This is my PhD student, Sangun San, and he actually worked on this project as a primary author, and he actually used his photo to visualize what's going on actually. So we are capturing all the features related to his face, like eyes, nose, ears, mouth, and then we actually want to obfuscate his eyes with a sunglass. And then to do that, we are actually changing some features in the latent vector, and we actually put these sunglasses in X prime. And this is what we want actually. We have one website fingerprint, and we want to change those features in the latent vector so that once we have an Amazon, it will look like a Google or maybe Facebook website fingerprint for an attacker in real time. So we are actually doing some feature manipulation in the latent space with variational autoencoders. So the idea here is that, for instance, we have Amazon and Google, and this is a very simplified clustering, all those website fingerprints, 100 website fingerprints, 100 website fingerprints. And our purpose is to move the mean of this cluster to the other cluster that we have in the latent space. So we have some mathematical explanation or expression in the paper. I'm not going into lots of details in this case, but our purpose is that, okay, once we train a new model, it's not going to be easy to distinguish these two website fingerprints for an attacker, and this is the idea. So, okay, we created these noise templates, okay, like we are actually moving all these websites from one cluster to another, half of them, and so on, and we are creating these noise templates. After we create these noise templates, we notice that, okay, we have these noise templates, but some websites have high activity, and we are trying to convert them into a low activity one. How are we going to do that? Like we need to introduce some negative noise so that we will lower the activity for that specific website. And we notice that it's not easy to do because whatever we have in that website, it's going to be rendered. So the cache activity will be always there. Therefore, we noticed that, okay, maybe we should get rid of the negative values in the noise template. And this is what we are doing. So once we get rid of the negative values in the noise, and this is what we end up with. However, we noticed that it's not easy or it's not enough to obfuscate those website fingerprints with only the positive parts of this noise template. This is why we noticed, okay, maybe we should add some offset for these noise templates, and then we should try it again, maybe get rid of any negative values if we have still more and more negative values here. So we are shifting up the noise and zeroing out negative values, keep significant features, and this is what we end up with. However, in this case, it means we need to create lots of noise. So after we tried these noise templates and so on, we also need to find out what is the latent space dimension, like should we keep it at like 50, 100, 200, 300? Because these website fingerprints are very long, and we tried to find out what is the optimal dimension. We found out that, okay, 100 dimension for the latent space is great, and normally we end up with 93% success rate with this latent space features. And then once we introduce noise, we notice that, okay, we are actually going back to 6%, even though we retrained the CNN model with the noisy data set. And then based on this offset value, the success rate changes a little bit, and we end up with 4.8% for Chrome and Firefox around 1.3%. The question here is, how are we going to create this noise in real time? Because, okay, this was so far we only saw the simulated noise generation. However, how are we going to create this noise in actual cache structure in our hardware? So in this case, we came up with something called self-modifying code. This is something very interesting. Intel and AMD devices have this self-modifying code behavior. In this case, we are actually changing the code or changing the instructions that we are going to execute in real time. So we have a very aggressive prefetch mechanism in these platforms, in these microarchitectures, because they are trying to increase the performance. So it means they are fetching or reading lots of instructions ahead of time. And once you change an instruction that was already fetched into the execution units, then it becomes a problem, and the system stalls for a long time. And we noticed that these stalls actually create a very high timing for the cache structure. And we actually use this SMC behavior. We had different components, like how frequently we are gonna create this SMC, or how much or how long we are gonna wait for the next SMC. And we were able to adjust the height and width of the noise. I'm not going into the details, but if you are interested, you should take a look at our left web paper. And as a result, in the simulation environment, we were able to go back to 4.8, 1.3%, something like that for Chrome and Firefox. But in reality, we noticed that we still have some errors while we are creating those noise templates in real time. This is why we noticed that, okay, we are actually going back to 28%, 29% for the Chrome and Firefox browser, and for the Tor browser, the success rate is only 5.2% once the attacker is retraining the deep learning model with these noisy website fingerprints. So we are actually achieving 3 to 4 times lower success rate for the attacker. For the Tor browser, it's even higher, and we show that our case is much better than the previous work, and our performance overhead is only 9.5%. So I have one question, one second. How effective is DevWeb when dealing with websites outside the pre-profile sensitive set? So this is a good question. We also had some websites included, and this is called open world data set, and we collected additional 100 websites, if I remember correctly. And in that case, we were actually also lowering the open world data set detection accuracy as well. However, in that case, we are only changing those websites to some other websites, and our noise temp, and we are still using our noise templates that we created during the offline phase. So those noise templates become a little bit random for those open world websites that we don't have in our case. And it's still lowering the success rate, but not this much, let's say. So I think that's all. So it looks like I spent around 40 minutes. This is why I'm not going to talk about this FastSpec paper. However, one of my colleagues actually gave a short talk about this paper, Dr. Caner Tol, and you can also find it online on YouTube. So I'm gonna skip this one. And in this case, briefly, we are using generative adversarial networks to create more different types of spectra gadgets. And then we are using some BERT-based vulnerability detector. So this detector, deep learning based detector, doesn't create lots of performance overhead, and it's actually detecting all those different types of gadgets in benign assembly code snippets very fast compared to taint tracking or symbolic execution. So if you are interested, please take a look at the paper and his presentation. So I want to talk about this part, future work for AI, and then I'm going to conclude the talk. So of course, nowadays LLMs are very important, and LLMs have lots of different usages. Like first one is like code generation, of course. The question here is actually, can we create new side channel attacks with LLMs? So we have some how can I say like works or projects on this one currently, and let me say that it's not easy to create a new attack, just by only using a ChatGPT model. So it means you need more capabilities, like maybe you need to have more agents to work together to actually create some attack codes that have not been seen before. However, in this case, you need to pass lots of information related to hardware design. In this case, it gets more and more problematic, and you need to pass lots of information. How are you going to do that? Of course, we have like right now RAGs, like retrieval augmented generations, and so on. So this is very new, and it's going to be very interesting in the future, like how we can use LLMs, maybe even like creating different attack codes and so on, like in the same attack with different languages and so on. The second one is side channel secure cryptographic implementations. Can we create those cryptographic implementations with LLMs? So in this case, we need lots of feedback mechanisms. So we may need to do some more fine tuning for the LLMs to be able to create these cryptographic implementations. And in this case, are we going to introduce lots of performance overhead or not? It's also another question. Another one is vulnerability analysis for sensitive applications. So can we actually use LLMs by only looking at the assembly level of the code? Can we detect any vulnerable code snippets that might be vulnerable to some microarchitectural attacks as well? And hardware specific defense mechanisms, like can we create more secure hardware components against these types of attacks, especially for the, of course, open source hardware components? Like they are, I think these types of projects are more interesting for the RISC-V based processors and so on. Another one is explainable AI. Okay, we are using all these types of models, especially deep learning models, LSTMs, CNNs, transformer models nowadays. Can we actually explain them? This is also another question, because okay, we are using them. We don't know exactly what is actually captured and what is the exact mapping from the traces to features that we are learning in these types of models. Another one is transfer learning. I mentioned this a little bit, like we have different devices, different microarchitectures, and in these side channel attacks, we assume that we know exactly which microarchitecture will be used by the victim. What if the victim is using another microarchitecture? In this case, can an attacker create a unified machine learning model or use some transfer learning to train another model for each microarchitecture, so that we don't need to collect the entire data set from the beginning for website fingerprints, for instance, and then train a new model for each different microarchitecture? So transfer learning is also very interesting in this case. And the final one is, of course, intrusion detection systems. We have lots of models also for these hardware security defense techniques. But the problem here is that, are they secure, or secure against adversarial attacks? Can an attacker actually learn what's going on in that machine learning model and craft the attack snippets in a way that these code snippets will not be detected as an attack anymore? And in this case, okay, I just wrote adversarial attacks, but I think these formally proved secure machine learning models will be even more important in these cases. Like, can we actually prove that in these conditions, this model is secure against adversarial attacks? I think it's going to be real difficult to claim that one model will be secure against all types of adversarial attacks, but maybe under specific constraints or conditions, okay, this model should be able to detect different types of adversarial attacks or adversarially crafted microarchitectural attacks. So this is my view. Of course, there will be even more different types of usages of machine learning and AI models in the future for the microarchitectural attacks. So thank you for listening. I think I talked about lots of different things. And if you have any more specific questions, and if you don't have much chance to ask me now, you can also send me an email. Thank you so much.
Thank you, Dr. Burke. Fantastic presentation. I think you touched whole pipeline of this adversarial attacks. Anyway, we'll leave the Q&A and see how the Q&A populates. And okay, I see a question now. What is the effectiveness of def web against attackers using novel machine learning architectures beyond CNN and LSTM?
So this is a good question. So we are assuming that we are actually capturing all those important features in the latent space in the variational autoencoders. So we assume that again, all those features will be collected and we will know what types of features will be also learned by different machine learning models. And our end goal is to convert one website fingerprint to another website fingerprint. So it is not very machine learning model specific, but it's more like website specific here because we have lots of different website fingerprints. We try to convert them to each other and we select as a noise template randomly every time in an application. So it means we assume that it's going to work better for autoencoders and different types of machine learning models. But of course, it should be tested, to be honest. And we didn't test it other than CNN and LSTMs.
How
So
is
how?
how is the noise injection tailored to different browsers like Chrome, Firefox, and Tor?
So that's one of the constraints in our case because those website fingerprints change a lot depending on the browser. Because like Google Chrome is using lots of different child processes at the same time. This is in general, it's a bit faster. However, Firefox is only using one process to render the website. In that case, the website fingerprint changes a lot. And this is why these templates are browser specific.
What is your perspective on quantum-inspired solvers here, for microarchitectures?
So for the quantum ones, I think it's very early to understand what's going on, like especially like whether we can actually run these types of attacks on the quantum like computers. There are some, especially for the memory structure, there are some attacks that I see, and and so I don't know exactly because like the cloud providers don't share those quantum computers between two users at the same time yet. But in the future, hopefully they will do that. And in that case, these will change a lot. These fingerprints, attack types, they will change a lot. And we will need to reverse engineer a lot as well because they are not going to release all that information in the future.
Going back to your question on features between across website, did you see any commonalities on certain, important features that you draw a line for your traces for site channel attacks? Is there any something we have students here who are listening and they're looking at their new dissertation topic or maybe new ideas to work on? What is your, what are you finding new and what are you finding common features in as you from your experience?
So for different browsers, same website, if the if the website is not rendering a lot of things, especially for instance, google.com, we see that there are some common features. However, if there are some websites with lots of rendering going on over an extended period, then the features change a lot. So we couldn't train a generic model for different browsers with a high accuracy, let me say. Like, okay, we actually captured maybe around 45 to 50% success rate for two different browsers. However, then it becomes more and more problematic when we increase the number of browsers like Safari and different things in the same microarchitecture environment. So I think it's an open research field now, like whether we can capture more common features from different browsers or not.
Super. I think and I don't see any other questions here. Is there any last words for new students or postdocs or looking at, do you anything you want to close the thoughts in terms of future topics that you would recommend for them to explore?
So I think, yeah, I mean, the LLMs for the side channel attacks, I think it's the next one, but I think it not only performing some, or finding out whether LLMs are actually learning new, so no, let's say whether vanilla LLMs can be used for these types of attacks or defenses, but like I think fine-tuning them, RAG, like new technologies, like how to use the reinforcement learning, for instance, in these types of attacks. I think it's something very interesting, and I'm personally interested as well because like it's not clear how to fine-tune those LLM models for these types of attacks. Like, for instance, recent DARPA AI competition, like they are also using some fuzzing approaches, those winner teams, or some reinforcement learning, fine-tuning a little bit, and so on. So those additional methods on the LLMs and combining all of them together is very interesting for the future work.
Super well said. Thank you, Dr. Burke, for your time this morning with us. I think you will receive a nice plaque from UND. I appreciate again so much for taking the time to do this webinar for us. I look forward to working with you maybe in future and on finding a way to connect with you on some proposals. Thank you so
Yeah,
much for.
sounds great. Yeah, thank you so much for the invitation. Hopefully, this presentation will be useful for all those students who are interested in this sidechain attacks. Thank you so much.
Super. Thank you. You have a nice day.
You too.